Hello everyone. In this lecture we will be discussing how we can perform convolution on volumes. By volumes I mean to say that we will have images that look like this. And how we can make the images look like a volume? We can make it look like a volume when we will consider RGB images. In earlier lecture what we were doing was we were discussing only grayscale images which has only single band, whereas in case of RGB we have 3 bands. So we will form these RGB channels in a form of a volume which is given like this. That is, we will cascade RGB plane one behind the other and we will form a cube or a volume out of it. So it will have a dimension of 6 cross 6, which is already, it will be the same for all the three planes. And since we have 3 planes, that's why we are putting it as 6 cross 6 cross 3. That's why 3 is over here. So please note that for each of the plane, that is for, this is for, let us say R, this is for G, and this is for B, we will have 3 different filters. That is, this is for R, this is for G, this is for B. So 3 different filters will again form a volume like this. That is, it will again form a volume like this, and this volume will be placed over this volume like this. And then we will perform convolution where each of the individual elements will be multiplied. By saying that means 4 will be multiplied with the 1, 9 will be multiplied with 0, for 2 will be multiplied with -1, and so on. And for the green channel which is over here, the pixel which is present in this green channel will be multiplied with the pixel in the green channel over here. And similarly for the blue plane also, that is, this pixel in the blue plane will be multiplied with the pixel at this particular blue plane. And all these individual elements will be multiplied, added together, as you can see over here, where we are multiplying this block with the red one, this one with green, and this one with blue. And then all of this will be added, and the resultant will be, for example, if it is given as 2, will be placed over here. And when we perform shifting of this box, we will shift by 1 unit to this side or 2 units on this side, depending upon whether the stride is 1 or 2, and we will move this box onto this 3D volume. Once it reaches the boundary to this side, it will move down like this by 1 unit or by 2 units, depending upon whether the stride is 1 or 2 respectively. So this is basically convolution of the 3D image, and you will and this results in a 2D image. This is very important. That is, a 3D image results in a 2D image when we convolve this 3D image with a 3D filter which is given over here. And the important part is, if the image has 3 channels, then the filter should also have 3 channels. That is, the filter should also be of like 3 cross 3 cross 3. So this should match this. If the image is of 9 channels, like in case of hyperspectral images, then the filter should also be of 3 cross 3 cross 9. So when these two will be convolved, it will result in the 2D image which is like this, having single channel. So this shows the convolution on the volumes with multiple filters. So this image is showing that, and this is somewhat similar to the one that we have discussed over here, but in that case in this case what we had was a single grayscale image, and we were convolving with multiple filters that detect diagonal, horizontal, vertical and horizontal edges. So in the same case, when we extend this idea of grayscale image to volumes, it will be like this. So as you can see, we have 2 different filters. Let us say this filter detects the diagonal elements and this filter detects the vertical elements of this image. So when we convolve this 3D volume with this filter, it results in a 2D image, as we have discussed here also. That is, the convolution of 2 volumes will result in a single channel image. So this operation of convolving these 2 3D volumes results in a 2D image which is given over here. And similarly for this also we will obtain a 2D image given over here. So these 2 images, this one and this one, will be placed one behind the other to form a volume which is of size 4 cross 4 times 2. So this 2 corresponds to the number of filters that you are using in a particular layer which is over here. So here we are using two filters, that is this one and this one. So that's why these two is coming over here. And also note that since it has three channels, which is RGB, so each of the filters that we are considering also has this 3 over here, which should match the number of channels in this particular image, which is here. So when we apply 6 cross 3, 3 cross 3, then the resultant image is of size 4 cross 4, and these two images will be sandwiched to form a volume which is given by 4 cross 4 cross 2. So this shows the convolution of volume with multiple filters. So it may detect horizontal line and it may detect vertical line. So these two features are cascaded over here. So this volume will be passed further through the next layers for more complex processing. So this again shows the same image that we have already discussed over here in the expanded version, with a subtle difference. And that subtle difference is we are adding a bias to this feature map that we have obtained through convolution over the volumes, and then we are applying ReLU to it. So once we do this, we get the modified feature map of this one over here, and this we will be passing it to the next layers for further processing. So this whole operation which we are showing over here is represented in a concise form like this. As you can see, this is a box which represents 6 cross 6 cross 3, which means that it's a RGB image having a dimension of 6 cross 6 and 3 channels which are RGB, and then it results in a output volume which is a 4 cross 4 cross 2, means it has 2 channels, as you can see over here. Ideally it should be not 4 cross 4, this should be actually not 3 cross 3, it should be 4 cross 4. This also should be 4 cross 4, and this also should be 4 cross 4 cross 2, and this also has to be 4 cross 4 cross 2, and this also has 4 cross 4 cross 2. So this is basically a typo, so I have corrected it. So this is 4 cross 4 cross 2 over here, and all the specifications like filter size, stride, pooling, and how many filters that you are using to convert this volume to this volume is written normally over here below this arrow. So because we are using two filters, that's why this 2 is replicated over here. And this we have already discussed, that is the filter size, stride, and padding in details in our earlier lecture. So this represents a concise representation of all this flow that is shown over here. So this thing should be always in your mind, but you have to represent it through this. Or if you are reading any paper regarding convolutional neural networks, you will see these type of images, but at the back of the mind you should have this type of flow going in your mind. So a typical CNN network is shown over here, and as you can see, it's a typical CNN network which is available in all, which is normally shown in most of the research papers and in even the text also. What is this network is all about? It is basically consisting of one of the input image which is of size 39 cross 39, and this is showing the number of channels of this image, which is over here. So there are 3 channels, so 3 channels will be of RGB, and if it in case it is a hyperspectral image or any other image which is of multi-dimensional channel, then it will be 39 cross the number of bands that it has, that is the number of channels it has. So if it is 16, then it means it is having a 16 channel or 16 bands of size 39 cross 39 image dimension. So when we do the convolution with a filter of size 3 cross 3 and stride of 1 and padding 0, and we are using 10 filters, so the transformation of this to this volume basically will become 37 cross 37 and 10, and this 10 is coming because we are using 10 filters in this particular layer, and this 37 and 37 are coming because of the formula that we use is n plus 2p minus f over stride plus 1, and we are creating a ceiling function of this. So when you use this formula here, n is 39 and there is no padding, and a filter scale is 3, and the stride is also 1, and then you add 1 over here. So what is the result? Result is 37. So that's why we have 37 cross 37 image over here with 10 channels. Again, when we do a filter convolution with a filter of size 5 cross 5 and the stride now is 2 with no padding, by saying no padding means we are using valid convolution. and again we are using 20 filters in this particular layer. So you can see here the volume, this volume is transformed to this with the third dimension changed to 20, and this 20 is coming because we are using 20 filters in this particular transformation. And this 17 is coming because n here is 37, padding is 0, and the filter size is 5, and now the stride has become 2. So if you put this into the formula which is given over here, you will get this, and this is equal to how much? This is equal to 32 divided by 2 plus 1, which is 17. So here it is 17 now. Now again you are doing a third layer of convolution, in which the filter size is of 5 cross 5, the stride is 2, padding is still 0, and now you are using 40 filters. So these 40 filters are reflected over here, and this 7 is coming because now 17 plus 0 padding minus the filter size is 5 divided by, now the stride is 2 plus 1, so this equals to 6 plus 1, which is 7. So it's a 7 cross 7 volume with 40 channels. So 40 channels are along this dimension, and 7 cross 7 is this. And similarly here we have 17 cross 17, and this is basically 20 channels, and here this is 37, 37, and this is 10 channels. So you can see how applying a convolution transforms the cube or a volume from here to here, and then this is transformed again in the layer 2 convolution to this box, and from this volume it is transformed back to this volume, which is because of this convolution layer which is at layer 3. So once you have this volume, you convert it into a single flattened length of one dimensional array. So this forms the fully connected layer. So you can have multiple fully connected layers, but here we are showing only one. So the dimension of this fully connected layer is 1960 cross 1. As you can see, 1960 is coming because you are multiplying 7 cross 7 cross 40. So this results in 1960 dimension vector. So it's a dimension of 1961. So this is number of rows and this is column. So one column with 1960 hidden units, and this is all connected to a logistic unit or a softmax unit depending upon your application, and which generates the logical output y hat. So this is basically a typical CNN network that we normally see in papers. So it will be a modification or the readjustment of these blocks. Maybe they will be using, so different people will be using different filter size, strides and paddings along with the filters. Depending upon their application, this network will change, but the overall concept will remain same. So the next important layer that we will discuss, that will be used extensively in convolutional neural networks, is pooling layer. So what is this exactly? So the pooling layer is basically, if you have this grayscale image, so what pooling layer will do is, it has two inputs. The two inputs are the mask size and stride. So these are the two inputs that are required for pooling layer, and this mask size and stride corresponds to the filter that we will be using in pooling layer. So by saying mask size is that if you have a mask size of 3 cross 3, then it will be represented by this. So it will be a 3 cross 3 mask, and by saying stride means how many jumps it will make towards the vertical and the horizontal directions, like from jumping in horizontal direction or jumping in vertical direction. So pooling layer is basically two types. One is max pooling and another one is average pooling. So these are the two types of poolings. So in case of max pooling, for example, if you consider here this image, which is a grayscale image, what max pooling will do is, it will lay an arbitrary mask over here like this, and then it will select the maximum value in this mask. So what is the maximum value here? So the maximum value is 9. So that 9 will be replicated over here. Then what will happen is, this mask will jump to this position. So it will be now in this new position here. So what is the stride for doing this? The stride for doing this is 2. So this means it is jumping by 2 locations. Then only this mask will come to this position here. And again it will calculate the maximum value in this particular small neighborhood, and the maximum value is 5. So that is replicated over here. Now it will jump to the downside or in the vertical direction here, and the new mask that will be obtained will be like this. And now the maximum value for corresponding to this situation will be 6, so it will be over here. And similarly for this mask where it will be giving you a value of 8. So as you can see here, the two specifications that which I just discussed, that is the mask size and the stride, in this case is how much? The mask size is 2 and the stride is 2. And what is average pooling? In average pooling, what will happen is it will try to find the average value in this particular mask. So the average value in this particular position is 6, so that's why 6 will be here. And in this case it will be 3.3, and in this case it will be 4.3, and in this case it will be 5.3. So this is the concept of average pooling, which will average the values of the image pixel which are present in that particular mask. So this is basically pooling. What is the main function of pooling? The main function of pooling is to reduce the dimension of the image. As you can see here, the dimension of the image is 4 cross 4, so it reduced to 2 cross 2. And one thing is important here, that the formula that we discussed, that is n minus f plus 2p over the stride plus 1, and the flooring function for that is applicable here also. So once you apply for this particular example, what is the value of n? N is 4. What is the value of f? F is basically the mask size corresponding to this pooling layer, so it is 2. And what is the padding that we have done? We have done no padding. How about the stride? Stride is 2 and plus 1. So what is the value here? It's actually, the value is 2. So this 2 is the size of the resultant image that will come out because of pooling. So the pooling operation basically reduces the dimension of the image also. So that is the main function of pooling, to reduce the dimension. This case corresponds to the RGB case, where we have 3 different planes. One is R, this one is G, and this one is B. What we have to do in case of this is, if we are using a max pool, then what we have to do is we have to do max pool for individual planes. Like here we have for R, so the value of the maximum value is 9. Here the maximum value is 6, and here the maximum value is 8, and so on. So basically what will happen in pooling operation is that the pooling operation has to be done individually on each of these slices. It's not like that of convolution where we were actually using this complete volume of like this. So in case of convolution, we were considering a complete volume like this, as we have discussed in our earlier slide. But in case of pooling, we don't do this. What we do is we consider each of the plane individually. So R will be considered individually, and at the back side of it we have a green plane. So in that green plane, whatever will be the maximum value, it will be filled over here at this point. And at the back side of it, again we will calculate the max operation, keeping that plane into consideration, that is the blue plane. And in that case, whatever will be the maximum value in the blue plane will be replaced here. So this means in case of RGB image, the max pooling actually operates on each of the individual planes and not in the form of a volume as it was in the case of convolution. So this is important, and please note that. So the concept of pooling layer is finished, and you will see that this pooling layer will be used a lot somewhere in between these convolutional layers also. So we will see that in our coming slides. But before going further, the important point that I wanted to discuss here is the advantage of pooling. So the advantage of pooling, which we have already discussed, is it reduces the dimension of this cube. So as you can see, once you pool this cube, the dimensions are reduced by 112, but this channel remains the same. So this is important. The channels of this cube will always remain same, but the pooling operation will always reduce the dimensions. As you can see, 224 is reduced to 112 cross 112. And the physical interpretation of this is that if you have an image, let us say here, which has some edges. So you can see these white patches. These are the features that are being detected when a particular image is passed through multiple convolutional layers. So at the output of some specific convolutional layer, you have these specific features that are coming out of it. So if you downsample this image, these features will still be there, and these are the only important features that we want. Rest of it is not important at all. So by reducing the dimension of this image from here to here, we are still retaining these edge features, and we are saving lot of computation time. So that is the main advantage of pooling. So what pooling is doing is, it is reducing the computational time by downsampling the image, and also it is able to retain the specific image features that are captured during the convolutional operation. So that is the main target of pooling, that is downsample. So this is basically a physical interpretation of what I have just discussed. So let's discuss a practical implementation of all the concepts that we have learned in this particular architecture, which is LANET 5 architecture. So in this LANET 5, we have this image which is of dimension 32 cross 32 cross 1. So please note, this one corresponds to a single plane and it's a black and white image. So what we are doing now is, we are actually applying an operation of convolution where the filter size is of 5 cross 5 and its stride is 1. And please note, here we are using valid convolution. So by valid convolution means there is no padding. So if that is the situation, if we apply this formula, which is n minus f plus 2p over stride plus 1, the floor function of that, then if we put these values, what will be the answer? It will be 32 minus 5 over the stride, which is 1, plus 1, and we are using flooring function for that. So the result is 28. So this is the output. So 28 is over here. So we are getting 28 cross 28 image, and please note, this is 6 and here it is 1, and the reason for that is we are using 6 filters in the convolutional layer. So that's why this 6 is coming over here. It's not given here, but you can write it as NC equal to 6. This means you are using 6 channel filters. So that's why this 6 is replicated here. Now we are doing average pooling. So in case of average pooling, what is the size of the filter that we are using is 2, and the stride that we are taking is 2. So in this situation, if we apply this formula again, then it will be 28 minus f is filter size, which is 2, divided by 2 plus 1. So what is the value? The value is 14. This is basically over here. And please note that at this situation, the channels will remain the same, because pooling will not affect the channels, as we have discussed in our earlier slide. Similarly, when we do convolution with a 5 cross 5 filter and s is equal to 1, and please note, here also the padding is 0, you will get 10 as the answer, and you can cross check with this expression over here. And when you do the average pooling by 2 and with a stride of 2, the filter size will this filter will reduce the dimension of the image to 5 cross 5, whereas the channels will remain same. And then we flattened out this 5 cross 5 cross 16 into a 120 hidden layer units, and then we have again 84 units of hidden layer, fully connected layer on the other part, and these fully connected layers are connected like a simple feed forward neural network. And at the output we have this softmax unit which converts these outputs into the labels. So this is basically a flow of a LANET architecture which we have discussed. Two things to be noted over here is that the cubes that are over here, that is 1, 2, 3 and 4, what you observe is that the dimension of this cube keeps on reducing, as you can see, whereas the channels are increasing. It is increasing in this direction, that is the channel width. So this channel width is keep on increasing, as you can see it's increased. Here also the same. Here though it is same because it's 16, but it started with the earlier channel as 1 and ended at with 16, whereas it started with a image size of 32 cross 32, but it ended with 5 cross 5. This is the important point. And the second important point is that during the backpropagation, we do backpropagation of this to update the weights. So at that point, whatever weights that are associated with the filters that we use in the convolutional layer will be updated, but in case of pooling layer, the weights that are available in that will not be updated because there are no specific weights corresponding to pooling layer. So pooling layer will not be taking part in any of the back propagation process, whereas the filter weights that are available in the convolutional layer will be updated during back propagation. So these are the two important points that I needed to discuss here. So in the next lecture, what we will do is we will understand the back propagation of convolutional neural networks. Thanks for watching my lecture. See you next time.